Hello, in this video we're going to look at some further pattern recognition in sequences. So in this section we will examine some more sequences given by the first several terms, and our goal will be to try to write out a formula, either an recursive or explicit formula or both for these sequences. We've seen that if we let the degree go high enough, there's always a polynomial sequence that will match the given sequence. However, most of these will have, actually all of these, will have another sequence which is a better and simpler fit. So basically we're looking to recognize some pattern and then describe it with a formula. Along the way we will be introducing some notation that will be useful to us later. So basically I have 5 things in this exercise 11, actually really 5 exercises. Just write out the next 4 terms and determine a formula for each of the following sequences. Of course, to do that, you're going to have to find some sort of pattern. So I'm going to suggest that you stop the video at this point and spend some time with these sequences. See if you can write out the next few terms, come up with a formula. It might be recursive or even better yet, explicit. So I'll leave it to you to do that. Come back when you think you got answers and we'll go over these. Press pause now. Okay, well, let's see. Let's take these one at a time. The first one is actually a very important one for us. It's actually something called a factorial function. So basically, we have a special name and notation for it. A sub k is called k with an exclamation point. Exclamation point is called the factorial. So this is k factorial is the way we would read that. In the sequence above, we have the values of the factorial function for the natural number inputs. So it's 1 factorial, 2 factorial, 3 factorial, 4 factorial. Well, recursively, what are we doing here? We're taking 1, and then term 1 is 1. Term 2 is 2 times 1, which is 2. Term 3 is 3 times the 2, which is 6. Term 4 is 4 times the 6, which is 24. So what you're doing is you're taking k, here's the recursive formula. A sub k is k times a sub k minus 1. So it's the term number times the previous term. Okay? So if we write that with the factorial notation, the recursive thing on the factorials is that k factorial is k times k minus 1 factorial. And one thing I want to point out about this is order of operations. Because of the parentheses, we'll do k minus 1 first. But factorial takes precedence over multiplication. So you don't multiply the k in the k factorial and then you don't multiply the k in the k minus 1 and then do a factorial. You do the k minus 1 factorial and then times the k. So for example, 4 times 3 factorial means take the 3 factorial first, which turns out to be 6, and then multiply it by 4. We do not multiply the 4 and 3 first, get 12, and then factorial. We can also view it as a product of natural numbers from 1 up to and including k. Now, by the way, we also can extend this idea for one other number besides natural numbers, and that's 0. 0 factorial is defined to be 1. So recursively, we could actually set it up with that as like our initial term, and 0 factorial is 1, and the k factorial is k times k minus 1 factorial for k's in the natural numbers. But k factorial can also be thought of as the product from I equals 1 to k of I for k in the natural numbers. And another way, of course, what this means is, I'll write this out here. What this means is 1 times 2 times 3 times 4 all the way up to whatever k is. That's what that product notation means. So 1 factorial is 1. That was our first term. 2 factorial is 2 times 1 factorial, or 2 times 1, or 1 times 2. That's 2 for our second term. For our third term, okay, we had 3 factorial, which is 3 times 2 factorial, or 3 times 2, which is also could be think of as 1 times 2 times 3. Either way, you get 6. 4 factorial is 4 times 3 factorial, which is 4 times 6, or 1 times 2 times 3 times 4, which is still 24. And so forth. You can see these kind of written out here. And so forth. You can see, all the way down here to where we were. So I think the sequence left off at the 7th term, 7 factorial. So for example, if we want the next 4 terms, 8 would be 8 factorial, 9 factorial, 10 factorial, 11 factorial. So 8 factorial is 8 times the 7 factorial, 8 times the 5,040, which is 40,320. Multiply that by 9 to get the next term, 362,880. Multiply that by 10 to get 3,682,800. And multiply that by 11 to get 39,916,800. So this factorial grows very quickly. Okay. And so that growth is actually faster than an exponential function. An exponential function would just be multiplying by the same number every time. But eventually, factorial, you're going to start multiplying by numbers bigger than whatever. So let's say you had 8 to the n, or 8 to the k for your exponential. Well, these first few terms we're multiplying by numbers less than 8. But once we get to 8 factorial and on up, we're multiplying by something bigger than 8. And so eventually it's just going to outstrip even the fastest exponential growth, which, as you already know, is very fast growth. Eventually starts slow and picks up. So this is a little bit slow, but picks up very, very fast, very, very quickly. All right, and that factorial has a lot of uses. You can see some of my notes on probability statistics and algebra for some of the uses, and we're going to use it a little bit later in this class. So this next one, the blue part here, is what was given, just to remind ourselves. We're going to see a separate pattern for the numerator and denominator. The denominator is pretty easy. It's just powers of 2 to the first, to the second, to the third, to the fourth. So it's just 2 to the k in the denominator. And the top is just a linear pattern. It's going up by 2 each time, so it's arithmetic. So that's just 2k plus 1. So a sub k is 2k plus 1 over 2 to the k. That's recognizing basically an arithmetic pattern for the numerator and a geometric pattern for the denominator. Now this next one here, here's the blue stuff, here's what we were given. The first thing is, notice it's alternate sign, negative, positive, negative, positive, negative, positive. An easy way to take care of that is just to put a factor of negative 1 to the k power. When k is an odd number, this will be negative, so the first, third, fifth terms and so forth will be negative, but when k is even, that will give us a positive. As long as we put that factor out front, it's times the whole thing, then that'll take care of the alternating sign. So now let's just not look at the sign, look at the numbers inside. Let's look at the denominator. Well, let's look at the numerator first. The numerator just goes up by 10 each time. So that's clearly just a linear or arithmetic pattern with a slope or common difference of 10. So that's just 10k minus 6. One way to see the minus 6 would be if we were to back up to a 0th numerator on the 0th term, which is not really there. We'd have to subtract 10 from this, which would give us negative 6. So this should work out. K is 1, that gives us 4. That works out. K is 2, this is 14, and so forth. So that's going to work out. The denominator, we might well do the same thing, see what the differences are. Here we saw the differences were 10 each time in the numerator. What about the denominator? Well, the difference here is 2, then 4, and then 8, 16, and 32. Okay, wait a minute. 2, 4, 6, 8. That's 2, 4, 8, 16, 32. Those are the powers of 2. When you have a geometric sequence, its differences will be in turn a geometric sequence. So this suggests that maybe we have a geometric sequence. So that's not quite, right? Because if we divide a term by the previous one, we don't quite get the same thing. But if you look carefully, they're just off of this geometric sequence by just a little bit. In fact, they're all powers of 2 just plus one more. See, that's take that 2 and add 1, take that 4 and add 1, 8 add 1, 16 add 1. So it's actually just 2 to the k plus 1. And so you can see that as you go across. So the next denominator, so this is 64 plus 1, this is 128 plus 1 is 129. 256 plus 1 is 257. Double that's 5,000. Let's see, 256, double is 512, but add one more is 513. Double 512, and you get 1,024, but add one is 1,025. And the top, we're just adding 10 each time, so that's a little easier. 64, 74, 84, 94. And again, our signs alternate. We were positive on the last one, so it's negative, positive, negative, positive. Now the next one's a super simple pattern. 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0. So that pattern is just going to keep going. Okay, but one way to generate this sequence is if we take the term number, divide it by 4, and put the remainder in there. 1 divided by 4 is 0, remainder 1, and so forth. 2 divided by 4 gives you a remainder of 2. 3 divided by 4 gives you a remainder of 3. 4 divided by 4 gives you a remainder of 0. 5 divided by 4 gives you 1, remainder 1. 1's the remainder, and so forth. So a notation that we can use here is called modular notation. So I thought I'd show you that. It's kind of useful here. If two whole numbers a and b have the same remainder when they're divided by some natural number n, we say they are congruent modulo n, and we write it this way: a is congruent to b mod n. Therefore, we can describe the sequence like this. A sub k is 0 if k is congruent to 0 mod 4. A sub k is 1 if k is congruent to 1 mod 4. A sub k is 2 if k is congruent to 2 mod 4. And a sub k is 3 if k is congruent to 3 mod 4. So these four numbers just keep repeating over and over and over. And since we're starting with k equals 1, we're actually starting with 1. So 1, 2, 3, back to 0. 1, 2, 3, 0, 1, 2, 3, and so forth. So if you understand that, then we can easily jump directly to a term. For example, a sub 127 is going to be 3. So let's see, why is that? Well, if you divide 127 by 4, it actually doesn't matter what the quotient is. The remainder is 3. That's what's important. So the remainder is 3. So you look down here, when you divide by 4, the remainder is 3. That's the last line, so the answer is 3 for that term. And this last one, let's see, 1, 0, negative 1, 0. Okay. So it was, here was the terms. It was 1, and then 0, and then negative 1, 0, positive 1, 0, negative 1, 0. Of course, then it'd be positive 1, and another 0, and negative 1, and another 0, and then positive 1, and so forth. Okay, so what's happening here is every other term is 0. In fact, it's the even numbered terms that are 0. Okay, so it's 0, a sub k is 0 if k is congruent to 0 mod 2. That means it's an even number. It's divisible by 2. When you divide by 2, you get a remainder 0. Well, what about the odd number terms? Well, they're just either 1 or negative 1. When are they 1? Whenever you divide by 4 and you get a remainder 1, you're going to get the positive 1, and when k is congruent to 3 mod 4, you get negative 1. So that's one way to describe this one. So if we want to go to a sub 1,525, first of all, it's not even, so it's not going to be 0. It's going to be either 1 or negative 1 because it's odd. Then we take it, divide by 4. We're going to see the remainder is either going to be 1 or 3. So it turns out to be 1 when you divide that out for the remainder. And so the answer is 1. Okay, so it's time to do a couple more homework problems with that.